What's worse, final exams take 45% of the total. And this is something.
Because we have.
But once again, you can use your ChatGPT to finish your take-home final. I don't mind because ChatGPT just say something weird. It's not answering the questions, so you can use ChatGPT. And but you cannot, for this take-home final, you cannot discuss with your classmates. You should work on your own final exam. And this is some information just in case you want to know. And it's super difficult because after the midterm exam, someone asked me, and is it that for the final exam, we were doing the same thing similar to the midterm exam, we get the final exam? No, that is not the kind, so dreamy final exam here. We are going to have a take-home final. Let me see. Now we are going to take a look at what we have left from the Monday. This is some things we have learned from the Monday. Is the fixed point method. And one thing I want to point out here is we say this is the fixed point method here, and then the fixed point methods we have several assumptions of function, and then the g should be continuous. And the gx, the domain, the range of the function is also in A, B. And here, if we have two assumptions on the g, and then the g has this one fixed point, and then this is the existence, and then this is the uniqueness. And then for the uniqueness, we have another requirement that is the g point. The theory exists, and then there's a k constant that is bounding this derivative here, and then this k is smaller than 1. And last time of the class, one student Wei Xing tell me, okay, he discussed with me, could we relax these conditions a little bit? If you go back to take a look at the proof of the theorem 2.3 on the textbook, and then you will see that actually we can relax this. We can actually relax these conditions, the requirements on the g prime x on the second conclusion here. Actually, we don't need the g prime x. It exists everywhere on the interval a b. Actually, we can use the Lipschitz continuous here, and then which means that the gx and then minus gy, and then there's a constant k, and then that is bounded by this one. And this is the and for any xy that is on the interval AB, and this is a Lipschitz continuous, and you can use this condition to replace this g prime. The derivative exists everywhere on the interval, and then there's the bound for the derivative here. But if you compare this condition, and then obviously this one is not. It's not. This one there's not so much restrictions on the g as this one. And if you take a look at if you compare the Lipschitz continuous and the g prime things, and then the derivative things, and then Lipschitz continuous, which means that it's a weakly differentiable function, and which means that the functions, the derivatives exist almost everywhere, but not everywhere on the interval. So this is more relaxed conditions on the g function, and this is something I just want to briefly mention, and it's not required And I just tell you, there's some discussions happening after the class. But let's go back to the example, and then we have, it's asking us to show this function has a unique fixed point. And if we take a look at the theorem 2.3 here, and then which means that we need to prove the existing, and also we need to prove the uniqueness. So now what I'm going to do is so first, I'm going to show the first things I just state here, the G function is a continuous function. And the second things, I need to show the range of the function. It should be the subset of the A and B interval. And now I'm going to show you this. So let's calculate the range of the function. What I'm going to do is to calculate the maximum and minimum of the function first. And this is the I'm checking the existence. So let me do this third part later. The third part is checking the uniqueness. And I'm going to copy them here. And now let's check the maximums and minimum first. So this is the first part. It's about the existence. And so this is a continuous function, and then it has the derivative here. And from the calculus class, we know that the maximum and minimum could be at the endpoints and the critical points. So now I'm going to get the critical point first. And the critical points, we are calculating the G point X, that is the derivative. And then for the derivative of this function is the x squared minus 1, and then divided by 3. And we got 2x over 3. And then we let that to be 0. And then we solve for the critical point. And then we get the critical point is x equals to 0. And now we evaluate the functions at the critical points and the both endpoints, and we got, so for the endpoints we get G negative 1, and then G negative 1 equals to 0 if we do the substitution, and then we get G negative 1 is 0. And then if we evaluate the G function as 0, and then we got negative 1 over 3. And then if we evaluate the functions at another endpoint, and then that is G1, and then it equals to 0 as well. So now we got the minimum. We should have already get the minimum and the maximum of this function. And this means that the minimum of the Gx, and then the x is in the interval -1 and 1, the minimum is just 0. And the maximums of the this function is just the this is -3 over 1 over 3, and the maximum is just 0. And this means that the range of the Gx function here is just equals to -1 and over 3 and then 0 interval. This is the interval we have for the range. And then this range, the range is a subset of the domain. So this means that we need the range of the function is a subset of the domain. And we check this happen, and then so we check the function satisfy the second conditions in the theorem, and now we can conclude that the fixed point exists. There exists at least one fixed point for this function. If you take a look at the functions theorem statement here, we just check this is a continuous function. And then we also check that the range of function is a subset of the domain of the function. And now we have already checked these two conditions, and then now we come to the conclusion that the G has at least one fixed point in the interval A and B. And so now let's get to the conclusion. The Gx has at least one fixed point in the interval A and B. So this is the first part, but the question is asking is actually asking us to find to prove this is a unique fixed point. So which means that we also need to check the second part, and we need to say, okay, the GW. So this is a more restricted version of the conditions on the G, and then most of the time we are going to check this part, and then we are going to see if the W exists on the interval, and then there exists a constant to bound the this W here. So now let's do this for this function Gx, and so this is the things here. We are going to check this one. Check uniqueness. Uniqueness. For the uniqueness, we have already got the derivative, and so what we are going to do is to get the absolute value, and then absolute value of this one is just the 2x over 3, and then doing the absolute value. And for the x, the interval is -1 and 1. So for this absolute value of the function, the derivative here is bounded by the 2 over 3. And for all the x in the interval -1 and 1. And so now, and for this constant k, this is the constant k in the theorem statement, and then this constant k is smaller than 1. So we can conclude that the functions has unique fixed point. And we can conclude that Gx has a unique fixed point in the A and B interval. Any questions how to check the uniqueness existence for the functions, the uniqueness and existence of the fixed point for a function? You can definitely check the Lifshitz continuous condition as well. Next, I'm going to give you more examples on this one and this part, but so now let's take a look at these questions again. And I'm going to show you that. So let's solve these examples, and then to see what is the what are the fixed point for these examples. So this is sometimes related to the theorem statement, and let's see. So if we solve for the Gx, Gp equals to P, and then if we want to solve this, the fixed point for the example 2, this is some further investigation in this example. But this is not the proof of the function of the example there. So for fixed point for the example 2, and then let's investigate into this. And we have, what's the definition of the function again? Is x squared and then -1, and then divided by 3, which means that we are solving this. X squared -1 divided by 3, and then equals to P. And if we solve this, and then this is equivalent to P squared minus 3P, and then -1, and then equals 0. You can definitely use the linear algebra knowledge to solve this. It should be like b squared 3 squared and then plus 4 and then square root and then over 2 and then that is the b minus this. And this is the plus and negative. And then this is 2 solution here. And it equals to the 2 over 1 and then 3 and then plus or negative minus and then square root of 13. And if you take a look at their values here, actually the P1 solution and then 1 over 2 and then 3 and then minus square root of 30. This one is actually belonging to -1 and 1, and that is the intervals we are stating here. And so this example here, and then it's actually ensure that we have a unique fixed point in the interval -1 and 1. But for actually we have another fixed point, but it's in another interval. And then for that function, for that another solution here, another fixed point here, that is the P2. It's 1/2 and then 3 plus square root of 13. And for this one, if you check the value, the numeric value of this fixed point, and it's belonging the interval 3 and 4. And now I'm going to check some things about the second fixed point about the function, and I'm going to focus on the interval 3 and 4. And if you take a look at the 3 and 4 interval, and then the g functions evaluate at the right endpoint, and this is just the 4 square and then minus 1 and then divide that by 3 and it's equals to 5. And if I check the derivative of the function and then evaluate at 4, and that is just the 2 times 4 and then divided by 3, and then is equals to 8 over 3. And which means that if you take a look at the value here, and then the derivative evaluate at 4 is bigger than 1, and then the G4 equals to 5. This is the image of the 4, right? Image of the 4, and then equals to 5, and which means that the range of the function G on this interval is not the subset of the domain of the function. And also the derivative of the function evaluate at the point here, and then we cannot find a constant k which is smaller than 1 to bound the derivative. So if you take a look at the conditions we have on the theorem 2. If you take a look at the theorem 253 here, and then check the conditions, all the conditions on the interval 3 and 4 interval, and then you will find out that it doesn't satisfy. So for the first one, it doesn't satisfy the first one. So the domain, the range of the G is not a subinterval of the domain of the G. There's another things does not satisfy, and we have the G point. We cannot find a constant k that is smaller than 1. It should be rigorously smaller than 1, and then bound such that the g prime x is smaller than or equals to k on the interval 3 and 4. So this is also in the interval 3 and 4. And we are saying the second case, and then in the interval 3 and 4. But although it does not satisfy these two conditions, and then we actually have one fixed point, unique fixed point on the interval 3 and 4. And this means that what does it mean? It means that so this criterion here, so unique fixed point, this is the conclusion. And then there's the criterion 1 here, and then the criterion 2 here. So the criterion 1, and then criterion 2, and then that is the A and B, all the Tyler plot here. And then, so I'm going to give you the things, what we get from this example. So if the function satisfy this criterion, and then we can definitely have the conclusions and to this one. But if this is a unique fixed point, and then we cannot say the function satisfy the criterion 1 and criterion 2. Does that make sense? So, which means that if you have already learned the map A, and you will see that these two criterions is sufficient, but not necessary. To guarantee a unique fixed point. Does that make sense? So this is one important things here about the unique fixed point. If you take a look at the unique fixed point, and then the interval is in, but you cannot say the functions on the interval satisfy these two criteria, because these conditions here are sufficient but not necessary. And so now I'm going to give you the one more things. Let's just go to the fixed point iteration, and then so now we already have the theorems at hand, and then we are going to use that theorem to generate a sequence of the number, and then that sequence of number is converging to that fixed point. So let's see. So this is the methods, and then all the things above is just introducing the fixed point problem and the fixed point theorem. And now this is the fixed point algorithm and fixed point iterations algorithm. Fixed point iteration algorithm. And we are doing this. So we have a function. So the goal is to approximate the fixed point of the function g. The fixed point of a function g. And we would first your input is to first choose your initials, choose an initial approximation, which means that just a initials point b0. And then second, we are going to generate a sequence of numbers repeatedly, generate a sequence of number, and then that is a Pn, and then n equals 0, and then infinity. And then by letting the by using this following formula here, and then the following formula is just the Pn is just equals to the G evaluated at the previous number, so Pn minus 1. And then this is how we generate a sequence of Pn, which means that we just substitute the results to the G functions again and again and generate the sequence of the number here. And if the if the sequence, so there's one assumption here in the algorithm first, but you later on you will check how we get this this kind of G function. So for this iterations, we can definitely have a sequence which is converging. But if this sequence is converge to G, converge to P, and the G function is continuous, you will see that the limit of the Pn, the limit of the sequence, is actually the fixed point. Why? This is because if the P is the limit of the sequence here, and then because the definition, this is for the definitions, how we generate the sequence of the number, and then this is Pn minus 1. And actually, because this is continuous, we can take the limit into the function's input. And because the limit of the sequence is just P, and then on the right hand side, we get the P, GP. Does that make sense? So for this part, it's because we are saying assume this sequence is convergent to P, and then so this is from the convergent text. But this part is from the definition, the Pn equals to the GPn minus 1. And for this part, we are going to use another assumption about the G is the continuous one. So if we take the limit of the G function for the points here, and then actually you can pick the limit into the parameters. If you have any questions here, and then you can go back to take a look at the definition of the continuous function. And so this is just from the definitions of the continuous function, or some property of the continuous function. And this part, once again, once after we take the limit into the parenthesis, the variable here, and then we can have the limit of the sequence, it is the P. And this is from the assumptions again. So this is the whole idea. We use the G function generate a sequence of the number, and then this sequence of number later on is converted to P, and we can conclude that this sequence, this P value is just the fixed point of the G function. But now the question is that there's one assumption here. If the sequence is converted to P, so the question is that how do we find out that G functions can generate such a converging sequence? So this is the questions. It is also answered by one theorem here. So there's one question here. So this is the if the sequence is converged to P, but the question is that how do we find such a function and then to have a sequence that is convergent to P? So the questions, how can we find a fixed problem and a fixed point problem, and which means that or the G function of the gx function, and that produces a sequence that reliably and rapidly converge to a value. Converge to the given root finding problem. And I'm going to let you take a look at one example here. People, so don't forget that the idea, the goal of this fixed point problem. Before we talk about the fixed point problems, any details of this part, and then you need to have to take a look at connections. Actually, the original goal of our problem is to solve the f function and then equal to zero. And then this is a root finding problem. And we just want to translate a root finding problem to a fixed point problem, and to use the fixed point iterations algorithm to find out the roots. And if you compare the fixed point iterations algorithm to the bisection iterations there, and then you will find out that if you find a proper function g, and then you will have a faster convergence result. And this is the benefits of the fixed point methods. You can choose your function, and then if you choose the functions correctly, and then you will get a faster convergence result here. And so let's see. So we are going to find the root of the function f equals to 0. So now this is an example here, but we are going to translate the root finding problem to the fixed point problem. So here, this is the things. I hope it works. Okay, it works. So this is one example. We are going to find the root of this function, and then the function here, the equation here is x cubed plus 4x squared minus 10, and then equals to 0. And for some knowledge, and we just want to test this examples, but we already know that there's a unique root in the interval 1 and 2. And now this is the problem. This is a problem fx. Let me just write down here. This is the problem, and then this is the fx equals to 0. And what we are going to do is to translate this problem to a fixed point problem. And then it's just equals to let the form, this is the fixed point form, and then it's x equals to gx. So the question is that how to find out this g function. Actually, we can have several different g function choices here. There are many uncountable but infinite choices of the function g. And if you take a look at one of the possible choices is, so we can manipulate the function, the equations in this way. So I'm going to put the 4x squared on the left-hand side, and then put the 10 on the right-hand side, put the x cubed on the right-hand side. And then next, I'm going to divide both sides by 4, and then I got this one, the x squared equals to this one. And next, I would get, I'm going to take the square root on the both sides, and I got this. This is the x equals to the right-hand side function. And if you compare to this one, and then the left-hand side is the x here, and then this is the gx function. And this is one possible choices for the fixed point format for this root finding problem. And actually, you have a lot of choices I just mentioned. For example, you can just add X on the left hand side and then add X on the right hand side, and then you would have something similar to this, and then do the subtraction for the equation, and then you will have something looks like this. This is another format, fixed point format for the root finding problem here, and we have like 5 options here, 5 choices here. They are all equivalent to this root finding problem. Does it make sense? So I'm going to let someone try here. So could you try? Could you prove that this one is equivalent to the root finding problem over there? This one, just try to do this one. So someone is nodding his head, so I'm going to invite him to write your answer here. We see. Try to prove this one is equivalent to this one. Yeah, just come here. I know you are super confident about this.
Just change it to the.
Yeah,
Okay.
you just try to prove the B format is equivalent to the this one, the root finding questions. Yeah, you are doing the square for both sides. Yes, and then you are going to multiply the X on the both sides. And then now you are almost done. Yes, that's good, super good, and then super confident and get a super correct result. So he just proved that the format B is equivalent to the root finding question here. He's doing the doing the square for the both sides, and then multiply the both sides by X, and then move the things around, and then we get the root finding question again. And then so that means that you can check the same things for the you can check with the similar process here for the format C, format D, and format E. And actually we can use the, once we have the G function here, the G function that is the right hand side part, and then we are going to use this G function to generate a sequence of number. And let's see, what do we have for the sequence of number here? The sequence of number we get out of your expectation. New page. Out of your expectation, and then we got this. So this is the A format. We start from the initial guess 1.5 because we already know there is maybe from some prior knowledge, we know that there's solutions in the interval 1 and 2. And then now the initial guess is 1.5. And then this is for the format A, and then this is for the format B, format C, format D, format E. And you will see that for the format A, after 4 iteration, is divergent to the 10 to the A magnitude number. And this one, after like the 3rd iteration, and then the number will become undefined because you cannot get the square root of a negative number in a real number set, right? And if you take a look at the C and D and E format, and then it works pretty well. It's just converging to the root is around 1.36523, and there's something. And then you see the C format, D format, and E format works pretty well. And if you compare this to the bisection wrapper, and then we have the same examples in the bisection wrapper. And for the bisection wrapper, it takes like 15 iterations to converge to the solution. And then, but if you take if you choose a correct format for the G, and then for example the D format and the E format, you just make 10 iterations, or just 4 iterations. 4 iterations to get the convergence result. And this is a good thing. So, but you will see that you need to choose a correct format to get a faster convergence result. if you choose a wrong format, it could lead to a divergence result. And so now the question is that how can we choose this correct G? And then what's the requirement for the G? And I'm going to just put the conclusions here. And the conclusion is some things. This is the fixed point theorem about the fixed point. This is theorem 2.4, and this part is the fixed point theorem, and it's telling you that when we will have a convergence result for the G function. And so there's one assumption. Once again, G is a continuous function. And then there's another be such that, so this part is saying that the range is the subset of the domain of the function. And then for all the x in the AB, this is the first part, and this is the same as the fixed point problem theorem just now, the existence and uniqueness. But here, all the things, the assumptions are quite similar. And then suppose in addition, this is again, that suppose that we have the derivative is this on the interval A and B. And once again, you can replace this part with the Lifshitz continuous condition here. And this is the constant K, and then which is bigger than 0 and smaller than 1. And it says with the, this is a bound for the, it says with the, this is the bound for the derivative here, G prime X is smaller than or equals to K. And for all the X, and then in the interval A and B. And then now, so if you have these conditions on the G, and then now we can conclude that the G function can generate a sequence of the number, and then that sequence of number can converge to one point. Then, and for any initial guess, initial guess P0 in the interval A and B, the sequence defined by, so that is just defined by the substitution Pn minus 1 and then equals to Pn, and then n is bigger than or equals to 1. And then for this sequence is converged to the fixed points, converges to the unique fixed points, unique fixed point on the interval A and B, in the interval A and B. And this is the theorem here. All the assumptions is the same as the existence and uniqueness problem, continuous, and then the domain, the range is the subset of the domain, and then the derivative is this, and it's bounded by a constant K, and then the constant K is smaller than 1. And then now if we generate a sequence of the number by the G, and that is converging to the unique fixed point, and this is the theorem, fixed point theorem. You could take a look at the, should I mention the proof next time? Yes, this is the very typical proof, and then I should mention this in the next class. And then if you check the function, if you check all the conditions of the G function, and then for the C format and the D format and the E format here, And then you will find out that the C format, D format, E format satisfy all the conditions we just mentioned in the theorem 2.54. And that's why we have a convergence result for the C, D, E, but not convergence result for the A and B. And you can check these things after the class. And this is all the things I want to mention today. And so wish you have a good weekend with the good grade of the midterm exam. See you. Oh, you will have a homework for your weekend as well. Happy weekend.
Did you wrote this or did you write one here?
Okay.
And after that, I have G prime and X one. And this one correct?
Yes, it's correct.
Okay. And for the homework, is there gonna be a new homework or is just the homework?
There's new
Homework
homework 6 about the fixed point and bisection method.
Is there a coding or no?
What?
A new coding or
It's
just the
not
homework?
coding this week. I think I will release another coding questions next week.
Okay.
Yeah.
Thank you. Hello，太多了。
我这个
我也是
这个
第二年是2，然后
回了，因为其他同学他也扣分，然后我发现这个错误也不大，是本来是要扣分的，他们也是扣了3分，也有人也是这样子算错，就是带错，可能就是数字有点小错，都是3分。
因为我看别人也是那个计算错，但是就扣1、2分。
可能他们也是带错了，然后他们可能如果是没计算错，可能有可能是他比较后面的答案错，你懂吗？
好吧。因为我前面都对了，但就只是带错了一个。
对。
OK， 好吧。结束了。
Is the coding the QR one, is that due tomorrow or next week?
It's due. I guess it's
Next week?
next week.
But then
Okay.
there's another one also assigned next week?
Oh, you do a QR code master? Oh, it's due yesterday?
No, not the homework.
Oh, the
code.
homework.
The
Oh, the
coding?
is next week.
And then there's another code assigned next week as well.
Yeah, next week. but
And that
not
one is
this
gonna be due the week after.
Yeah, the
Oh.
week after.
Okay,
He's just waiting for you.
Oh, so I just want to know the convergence rate of the iteration, the 6-point iteration.
Yeah, we were going to mention this tomorrow, and the next week is the last part,
Yeah, I just.
the convergence
Yeah,
results
I
here.
just.
So if you compare this one to the bisection method, the bisection method is 1/2 n. So which means that if you choose a smart function g, and then you can have a derivative bump here, right? It's smaller than 1/2, and then it would have a faster convergence result. So if you take a look at all the function here, this function is also, this is the 6-point iteration, but it takes like 30 iterations to converge. So this means that if you compare this one, this is also fixed point, but with another function g, right? It's faster convergence, which means that if you check the derivative of them, and then this one has a BAM that is less than 1/2. And this one is maybe it's bigger than or equals to 1/2. I think it's bigger than 1/2, this one. Let's see.
So that is the definition of big O, right? The convergence rate, because it can be read as
the
something
big O
smaller than
1/2, and yeah.
and if the function has the lower derivative, I mean the upper bound of the derivative is smaller, then does it will be converges faster?
What's the n?
Oh, just
Can you write that
maybe the derivative at Pn, because I just write it as a Taylor expansion of it. So we want to because this is the answer. So we want to just make this is small, and we know this will be small. So if also be small, there goes to 0.
Yeah.
faster. Okay.
So we just want a derivative that is has a BAM that is smaller.
Yeah. Okay. Thank you.
For the homework number 5, we can use the NumPy QR package, right?
Of course you can.
Thank you so much.
I hope you can use the lamp point.
Thank you.
Yeah.
It's just finding the agonized, right?
Yeah.
This function in Python.
The function, I have shown you the the reference web page.
Yes, yes.
Yeah. And then you can just
It's
use,
really short. I mean, the real coding should be short, right?
yeah, it's a
you can
recording, it's very short, it's just use that package and then switch the matrix.
我有个问题，就是
No,
当时我看到你先扣了分数 y 嘛，因为这个 square，然后这个 positive definite 它就会是 positive 的嘛，但我没有写出来，就我想知道如果是 final 的话是不是要
没有是可以的，不是我改的，因为
哦，
你懂吗？
谁改的？
是另外一个 numerical method 的人，不是归的，因为归的我不太信得过，我
TA 吗？
另外一个人吧，反正就
哦，
是
好好。
他那个人比较严格，然后他又不是上我这门课的，所以我就告诉他，我
你有
知道
检查是吗？后来
我没有，我让他第一份改念，我就知道。然后后来我发现他的那个 standard 太严了，因为
哦，
我知道你这个做的不错，所以我就让你自己也不想写 standard solution，然后让他先改你的。然后我发现他给你扣分，我就这个不用扣分，人家是知道，人家不说你。
OK，然后这个我发现它圈了一下，这儿不应该是负的吗
哎，他肯定是手滑了，他手滑了，
？OK，好，
他手滑了，他一直拿着你这份东西来当 standard solution 改，
哦，
手滑了，他手滑了。
好，谢谢。
啊，你们个个都说难。Everyone say this is some difficult, and then we got 100 in this class.
I just didn't finish it.
5 to 6.
I didn't finish it.
You didn't finish it.
Yeah, so.
That wasn't great for a Tuesday, Thursday class. That wasn't great for a Tuesday, Thursday.
One week. But it's super difficult. I just want to warn you.